Okay, last time you recall, we determined that the work done on a volume element delta V by a pressure difference delta P is just the product delta P and delta V. Potential energy change of a delta V is just mgy, mg times delta y, where m is mass density times volume increment, and kinetic energy is 1/2 mass times v squared. If we divide the volume increment out, we get this relationship, which immediately gives us this relationship. So this relationship is just another expression of the work energy theorem. And another form of the relationship is this, where we, instead of writing changes in these quantities, we write the first value of each quantity has got to be equal to the second value of each quantity, which is the case if the change in the sum of those quantities is 0. Now, looking at the questions B9, B10, and B11 from the January 15th, January 14th document, again, using the fact, Bernoullis equation. Our first question is, well, if y is constant and velocity goes from 1 meter per second to 2 meters per second, what's that imply? You should stop and work that out. You should read that problem and work it before you go on, especially if you weren't able to log into class today. Okay, well, the question then becomes, well, if y is constant, that means that the change in rho gy is 0, because rho and g aren't going to change. If y doesn't change, that does it. You have no change in rho gy, which means the only quantities that can change are the pressure and the 1/2 rho v squared. If v goes from 1 to 2 meters per second, then there's certainly going to be a change in 1/2 rho v squared. This is water, so rho isn't going to change. And if v goes from 1 to 2 meters per second, this quantity is going to increase. Since the change in this plus the change in this, no change in this, since the sum of these two changes is 0, an increase in this one results in a decrease in this one. So we work that out, and we find that, writing it out in detail, the change in rho gy is 0 since y is constant. Change in 1/2 rho v squared is 1/2 rho times 2 meters per second quantity squared minus the same thing at 1 meter per second. The rho is 1,000 kilograms per meter cubed, and factoring that out, we get this. I'm not going to read it to you, it's obvious. And we get a change of 1,500 newtons per meter squared. Okay, now that comes out 1,500 kilogram meters per second squared per meter squared. If you multiply the kilograms by the meter squared, divide by the second squared, and then a meter cubed in the denominator, you can convince yourself that it can be rearranged to this form, and this is a Newton divided by a meter squared, and that's going to give you units of pascals, units of pressure. So that this quantity goes up by 1,500 pascals or 1,500 newtons per meter squared, and I say delta P changes by, say P changes by negative 1,500 newtons per meter squared, or delta P equals negative 1,500 newtons per meter squared. Now, it's not completely intuitive that the pressure should drop as the velocity increases, but let's think about why that is. A typical case, we've got a pipe, let's say, narrowing at this point, or between here and here. Before the narrowing, the fluid, being water, can be moving at some velocity. If the pipe narrows, the same amount of fluid has to get through this pipe. It's got less cross-sectional area, so it's clear that it has to move faster. To increase its speed, something has to do work on it. Which one of these quantities corresponds to work being done? Well, it's the change in pressure. How does a change in pressure do work? Well, it exerts a force. Pressure exerts a force on the fluid here and speeds it up. Okay, so you exert pressure, you speed the fluid up, you do work, and now you've got less energy per unit of volume, which means you're going to have less pressure. Okay, use the pressure to do work, and that uses up some of the pressure in a sense.